guys, I'm Malia, and what I'm going to be doing today in this video is I'm going to be going over one of the tutorials that is given to you by OpenFoam. I'm going to be explaining the basics of each folder and what they mean, and what each script inside means as well. And then I'm going to actually do the problem and show you what it's like in ParaView and the different things that you can actually do in ParaView. So let's get to it. Go into Finder and then press Command-Shift-H or wherever you have your OpenFoam folder. We're gonna go into that. And in my last video, I showed you how you can copy all the OpenFoam tutorials into this tutorials folder. If you haven't done that or you don't have access to these files, then I would recommend to go to my previous video and watch that part so you can have access to this and follow along. So the one that I'm going to be doing today is in incompressible, pimple foam, and laminar, and it's actually going to be this offset cylinder one. So what I'm going to do is I'm going to copy it and I'm going to put it into my run folder so that way it's easier to access when I'm actually within OpenFoam. And before we do anything with it, I'm going to go in and I'm going to explain each one of these folders and what they mean. So every OpenFoam problem that you do, whether it's from a tutorial or one that you make on your own or find somewhere else, should have these three main folders inside: zero, constant, and system. And we'll start with constant. So if you click into this, for this problem, it only has the momentum transport and transport properties scripts, but some will have a polymesh folder, which contains a full description of the case message for each problem. It will also have more scripts inside that further explain the problem, such as any turbulence that happens. Another thing that could be in here is a geometry folder, which explains the geometry or has more properties of the geometry. But for this problem, we have the momentum transport, which is also known as turbulence properties for versions of OpenFoam before version 8. But what this does basically, it specifies the simulation type that you're using, which can either be one of three: laminar, RAS, which is also Reynolds averaged, or LES, which is the large eddy simulation. Depending on which one you have, you're going to have different settings below it. So if we click into momentum transport here, you'll see that the simulation type for this one is laminar, which means that there's no turbulence models used in this, so there's no turbulence at all. And you can see that it goes into more detail down here. So depending on what simulation type you have, you're going to have different, settings below it. And so there's that. And then there's also transport properties. So this specifies the physical properties. There's not much here, so this is just saying this is a Newtonian fluid. And that's most of the, or all of the constant folder. And now we're gonna head into the system folder. So this has quite a few things in it. The system folder specifies a lot of the problem. If we start with control dict, this has parameters for the problem, such as the start and end time, the tolerance, how many time steps you're going to be taking, and information for the output data. So how precise you're going to be, when you're going to stop, so on and so forth, what solver you're going to be running, which is right here. So there's that one. So now we're going to go into FV schemes. There's not much here. It just shows or it sets whichever discretization scheme you choose to use. And for us, the default is Euler, but as you can see, you can also play around with everything there. The next is FV solution. So what this contains is more tolerances and equation solvers and other like algorithm controls. And again, this is where your solver is specified. So here you can see that we're using ParaView. Other ones that we can put here are PisoFoam and SimpleFoam. And basically those three are used for, they're just the three different solvers that you can use. They differ in how they loop over the equations that they use, but they all have the same basic governing equations. And PimpleFoam, which is the one that we're going to be using today, is actually a combination of the PisoFoam and SimpleFoam. PimpleFoam is used for incompressible turbulent flow of Newtonian fluids. And PisoFoam is used for pressure implicit split operators. SimpleFoam is a semi-implicit method for pressure-linked equations, but we don't have to worry too much about these because we're not going to be using them today. If you did want to learn more about them, I can link the OpenFoam user manual below, and you can take a further look into everything that I'm talking about today, actually. So yeah, you can go ahead and do that. And obviously, if we have different solvers, then we're going to have different settings below it. So that's it for FV solution. And then another thing that we have in here is this block mesh dict. And this basically determines your geometry for your problem. So it specifies all the points. As you can see, there's quite a few for this one. And then this is putting it into like what shape you need to go on. So this is the 5, 4, 9, 10 that specifies, that relates to a point each. So up here, this would be 0.0, then 0.1, 2, 3, so on and so forth. And this just tells you how they connect in each way. And then again, this is just further specifying edges and then the boundaries. So what are faces? Are they to the left, to the right, down? And then obviously it's a cylinder. So we have this block mesh dict, and it is very important to the problem. It relates directly to the block mesh command, which it's actually a mesh generation utility. It actually reads this script and creates the mesh from it, and it generates the block stretcher that is specified. So this script can be found in either the system folder, which is where we are now, or if I go back to the constant folder, as I stated previously, sometimes they have a folder called polymesh. It can also be found in there. I think it's typically found in the polymesh folder within constant, but I know with my experience with OpenFoam, I have to have the block mesh dict in the system folder, or else block mesh will not run and it will not generate the geometry. I've looked further into this online, and as far as I can tell, there's no difference between running it within the polymesh folder or the system folder. So I don't think you have much to worry about there. And also, depending on what you're going to want to be doing for each problem, you might have other scripts in here, including snappy hex mesh dict or surface features dict. Again, those are different commands that we're not going to be running today. And if you want to look further into it, I have the user manual linked below. And then the last folder we have here is 0, and this is these are all the initial conditions of your variables. And the most common are the two that we have here, which is pressure and velocity. So if we go into pressure, we see that it specifies the type on each face, which is, these were specified in the block mesh dict. And the 0 gradient is the normal gradient of the pressure is 0. So that's all that means. And then fixed value means you can set it to whatever you want. So I could technically change this from 0 to a different number, but I'm going to leave it how it is. And then empty, this means that, well, OpenFoam typically solves cases in 3 dimensions by default, but you can change this to 2D by setting a boundary to empty on boundaries normal to the 3rd dimension. 0 is also used to set boundary conditions. And if we look into U, then you can see it's more of the same thing that we see in the pressure folder. No slip means that it's not moving. And other folders, we can have more variables within this initial condition. Like I said before, it just depends on what we're trying to solve for and what we're running. But an example of some other things we can have is a K script, which is for turbulence kinetic energy, or omega, which is for turbulence specific dissipation rate, or nut, which is turbulence velocity and is actually evaluated from the K and the omega. But those are for turbulence problems, and as I stated before, we don't have turbulence in our problem. So now that we've gone through everything within these folders, we can get started on actually doing this problem. So now that we're actually going to go ahead and start doing this problem, we're going to have to open up Docker. And if you're not signed in already, then you need to sign in. Not sure why it did that. And then we're just going to minimize this window because we just need Docker open. We don't actually have to be looking at anything on it. And then the next thing that we're going to open up is Xquartz. Oh. Okay, and to get to OpenFoam, we're going to type cd home/OpenFoam. And I'm running version 9 of OpenFoam, so I'm going to put OpenFoam 9, and then you're going to put -Mac OS, and we're going to be using ParaView, so we have to add a -P to that. And it's going to load. And again, once you see this, that means you're actually running OpenFoam within Docker. And I want to go into the run folder, so I'm going to type cd foam run. And now that I'm there, I want to actually get into the offset cylinder folder here. So I'm going to type cd offset cylinder. And now you can see that I'm within that. And what we're going to run is the command block mesh. We're going to run the command block mesh. And as I mentioned before, this reads the block mesh dict script right here, and it creates your geometry and the mesh. So we're going to go ahead and run that. Okay, and now that we have that run, before we do anything else, we can take a look at this in ParaView. And we can press apply. And you'll see this. You can go up here and you can look at the different variables that you can look at. So these were the scripts or variables that we saw in the 0 folder. We can look at the velocity here. right now it's on Surface, but wireframe is also nice to look at. Yeah, so here's this. Obviously nothing has been calculated yet, so there's no time steps that we can look at or anything, but this is just how the problem has started. This is the initial shape of it all. So now that we've looked at that, we can exit out of here. So before we run anything for offset cylinder, what we're going to do is we're going to make a copy of this, and we're going to name it to offset cylinder. So if we need to change anything within our offset cylinder folder, and we run it and something goes wrong, you'd have to start the problem over again, or if you want to rerun something, you'd have to start the problem over again. So instead of doing that, you have your original folder without any of the calculations, so it's pretty simple to go back. So we're just going to get into the offset, make sure that you're in the offset cylinder folder before you do anything. Okay, and once you're in the offset cylinder folder, what we're going to run now is ParaView. So this is the solver that I mentioned earlier. And it's the combination of the two other solvers. And once we run it, it's actually going to take a little while, so you can go ahead and pause this video and then come back after it is done running. So once it's done running, if we go into the offset cylinder folder, which is the one that we actually ran ParaView in, you'll see that there's a lot more folders added into it now. These are just like the 0 folder, but they're at different time steps. So if I go in, there's the P and the U, and there's also additional ones. But we're not going to be doing anything with these. So we can actually visualize what each of these steps looks like in ParaView, or ParaView, I mean. So again, we're just going to click apply. And again, the same shape that we saw originally pops up. Again, I'm going to click up here and I'm going to press U. Something else that we can also do is we can scroll down here. So what we're going to do is we're going to go down here and we're going to go underneath coloring, and we're going to press edit right here to edit the color map, because I'm not the biggest fan of the blue to the red. And you're going to see a bunch of these on the side. We want to press the one that looks like a little folder with a heart. And you can choose what you like. I prefer the blue to red rainbow because it's pretty bright, and it works really well to visualize what you want. And then if we just exit out of this, you can see the change that's made. And now we can also change it to wireframe like I did earlier. But this might be better with the surface for right now, because what we're going to do is we're actually going to go up to the top and we're going to look at the time steps. So what we can do is we can just press this middle one to go one type of step at a time and see how it changes. And you can see that's a pretty drastic change from the very first one. And you can just keep clicking through this until you reach the end, but obviously the max here is 40. If you don't want to click through every single one, then you can click this one and it jumps straight to the end. But as you can see, that wasn't much of a difference. The biggest difference was probably from the initial time step to the other one. And again, if you just want to go back to the beginning, you can click that up there. but we're gonna go to the end actually. So you can see it's pretty dramatic. We can also compare this to what the pressure looks like. So obviously it's very different, the pressure from the velocity. And again, it didn't keep that rainbow color because I didn't set it as my default or anything, but we can go and change that again if we want. So obviously the beginning step for 0, there's not much going on, but by the end, the pressure is pretty half and half. So it's on the lower end on the right hand side and on the higher end on the left hand side. So there's some different things that you can do within ParaView to analyze the results that you've got. I'm going to change it back to you. And sometimes also ParaView can be a little slow on the Mac. Obviously, if you watched my last video, it took a lot to download OpenFoam onto the Mac. And even though it does run well, sometimes it is slow. Like if I try and move this geometry, it's going to be a little delayed, as you can see. But now this also shows that the upper boundary doesn't have any pressure or velocity. We're looking at velocity now. And if I want to go back to how it was before, I'm going to click this little button right here, and it takes me back to how it was. So there's different ways you can analyze your geometry and your findings within ParaView. I'm just going to show 2 or 3 on here. So there's 2 different ways that you can access these. There's some buttons right here for the main ones. So there's contour, clip, slice, threshold, glyph, stream tracer, warp, group data sets. Or what you can do is you can go up to, I believe it's filters, and then you can see my recent ones show up here. You can also end up favoriting some, or you can just look at the alphabetical list. I'm not going to go on it because it takes up the whole screen. Well, here, so this shows all the different ones that we can use. The first one that we can do, we'll do glyph first. So that's this one right here. And again, that was just one of the buttons right here. So in order for it to be applied, you have to click apply, and all the settings for it are underneath that you can scroll through. But what glyph does is it shows a glyph, which these are a bunch of arrows. These can also be changed to cones, lines, everything, but it shows arrows at each point or cell where there's data input. And obviously you can see all the velocity is pointed to the right-hand side. And so these eyeballs next to each of the things, that just means that it's being shown. So if I click on this eyeball right here, it's going to close, and now I'm no longer looking at the glyph. So I can open it back up, and I can close this. And now you can see more of the arrows of the glyph. I would, well, I can try and rotate it. But like I said, it's a little slow, so I don't know how well, I don't know how well it's going to turn. So yeah, and obviously there wasn't, as we saw earlier, the top of this geometry was completely blue, so there wasn't any input, so the glyph wasn't going to be created on the edges. And again, I'm just going to click this little camera right here so that way I can go back to the front facing. So there is that, and I'm going to close the eye on the glyph now. Another thing that we can do is this stream tracer. And if we go back to this filters, instead of doing recent or alphabetical even, you can hit search, and then you can search for any any tool that you want to use. So we're going to be using Stream Tracer here, so we're just going to click this. And again, you can play around with a lot of this, with a lot of the settings, and just see how they work. Oh, that's not good. I want this eyeball open. And let me click apply. And this stream tracer generates stream fields in a vector field on the object. And again, you can see that it's loading down here. So if I turn this or try to, let's see how well it works. You can see it's kind of an odd shape. Oof. Kind of hard to see and play around with really when you can't move the shape that well. So let me just go back to how it was. But again, it's more of, it looks more like the same of the original. If I open this eye, it doesn't look like there's much of a difference, but it did look more rounded than our actual shape. So we have that. And another one that can also be really useful, which I'm gonna search for, is the plot over line. And I'm just gonna hit apply. And again, you can play around with this a lot. If you go here, if you go into the settings area, you can actually click what lines show up. So as you can see, the more I click, the more lines appear on here. And they do a good job at labeling all of it. But, oh, there's a better view now that we can, that big one is up there. So it really shows you all of these, and it's just another way to view all of your data, which can be really helpful depending on what type of problem you're doing. Again, you can kind of see that this is where the hole in the object would be, because it cuts out. But yeah, so you can see that the magnitude of the velocity kind of goes down and then really shoots up there. And yeah, that's a lot of, or those are just a couple of things that you can do within ParaView. Like I said, it's kind of hard to move the object around so you can really look at it, especially in Mac or on a Mac desktop, but it's easy to still move it, as long as I found it as long as you can still get back to the original viewing of it. So yeah, that was the basics of some of the things that you can do in ParaView, how to complete a problem within OpenFoam, and the basics of the folders in each of the tutorials. If you wanted to try other tutorials, there are plenty that you can choose from, as you can see in here, and I would encourage you to do it. Again, I'll link the user manual below so that way you can take a deeper look into OpenFoam and its programs and how it works. Thank you for watching.